Welcome back. We have a chapter in the handout from the TutorWeb which deals with the Bitcoin programming language. That's a programming language called Script, and that's what we're going to do now. It's used in most of the regular cryptocurrencies, including the Smiley coin, which we're going to use as our example. So let's go to a block explorer and look at some of the Smiley coin blocks. You can do this in any block explorer for most cryptocurrencies. You will see these blocks here. This is a generic explorer for many cryptocurrencies. There is also a special one for Smiley coin. But let's take the generic one. Let's pick one of these blocks which have a few transactions. Take one of those and look at what's inside them. So here's a transaction with lots of outputs. Click on that, look at the internals, and you'll see it takes a certain input, which is output from a previous transaction, sends it to a bunch of addresses. And now let's take a look at the raw transaction. So inside this, there are descriptions of the various outputs. Remember, this transaction sent 5 smileys to several addresses. And within each output, there is a small computer program. And there's also a hexadecimal version of the same thing. So here's a computer program which says something about duplication, something about hashing, something about comparisons, and checking a signature. So let's go a little bit through what this actually means. So here's our little book or set of notes. We're in chapter 23. And I want to start with a very short example of how the programming language works before we get into a real example. So here's a very nice small short program. It says take a 2, take a 7, add, take a 3, subtract, take a 1, add, take a 7, equal. Compare, in other words. And when this is executed, it's just executed in sequence from left to right, and there's no operator precedence as in ordinary mathematics. So 2 and a 7 are put on a stack, and after that, the stack contains a 7 and a 2. The add operator just adds the top 2 numbers and gets a 9 and sticks that onto the stack. So the stack now contains a 9. Then we have a 3, that gets pushed on the stack, so you have a 3 and a 9. And then a subtraction operator subtracts the 3 from the 9. Then you push a 1 onto the stack, and you add the 2, and you get a 7 on the stack. Now next we put another 7 on the stack, and we check for equality. And of course these two are equal, so the equals operator returns a true. So this is sort of a very simple example. It's in part borrowed from Andreas Antonopoulos' book, or the idea is borrowed from there. And if you want to get anywhere with Bitcoin or other cryptocurrencies, you want to start by buying Andreas Antonopoulos' book called Bitcoin. Now, to spend a regular transaction, you need to get something. You need to go back here, look at what this is. This is a script, and it's only a partial script. So to spend the transaction, you need to provide a script which goes on the start of this, and when prepended to this script, the complete combined script returns a true or a nothing else. So let's see how that works. We take a script, any transaction, and there's one right here. This is a spending transaction for a certain input transaction. And if you actually look at them, then what you will see is that there is a spending transaction which provides a certain public key. And that's where the trick lies. You need to provide a public key which, when hashed, results in exactly the hexadecimal string provided here. So what the program then says is duplicate the previous string. Now remember, we're going to provide the public key. Duplicate the public key, hash that using an hash 160 operator, and that operator, what that means is to first hash with a hash function called SHA-256, and then hash it again with an operator called, or a hash function called RIPEMD160. So you use two hashes to obtain an output of a certain length, and to make it a process which is extremely difficult to forge. So basically you need the public key to be able to provide the output that's required here. So to generate this output, you really need to have the proper public key and prepend that. And then you need to have a signature. So you need to provide a you need to have something which verifies the signature of this, and that's the last argument of this this program. Op equal verify. If you have provided the correct public key, then that got duplicated, hashed. Op equal verify. Compare the two hashes; they have to become the same, and then the last check signature is the way to get this little program to return a value of true, and that means you can spend it. So you can only spend it if you have the correct signature and you provide the correct public key. Now the thing is that once you spent it, then you have shown the public key, and that's why you also need the signature. If you guarantee that you would never use a public key more than once, then you wouldn't really need the signature. But this double checking means that in principle you can at least use the same public key more than once. So in other words, you can spend from the same address lots of times. It's often considered bad practice to do this, but it is perfectly safe since you're the only one who holds the private key, and therefore you're the only one who can sign the transactions. And that concludes our very short introduction. We will try to provide more short videos, and where we try to go over other aspects of the programming language and special features and things you can do with it.